In this video, we're going to be looking at density curves. The first thing we're going to look at are what's called random variables. So a random variable is simply a variable whose value is unknown, and in an experiment, there are certain values that are assigned to that particular variable. So we're going to look at a couple of examples. The first one we'll look at, let's just look at rolling a die. Okay, so rolling a die, you have possible values, we'll call them X, of 1, 2, 3, 4, 5, and 6. And the probability of rolling each one of those is going to be 1/6. And we could look at this distribution where each of these values is going to be 1/6, and let's start off, we'll start off at 1. Okay, 2, 3, 4, 5, 6, 7. So I'm going to put my 0 there. There's no chance we can get a 0 though. So you can see here we have a distribution, and each one of those values is very defined. The die is either going to be 1, 2, 3, 4, 5, 6. There's no chance you're going to get 2.5, 3 1/4. This is what's called a discrete random variable. And a discrete random variable takes on specific values. Okay, such as 1, 2, 3, 4, 5, and 6. Now, they don't have to be whole numbers. It all depends on the situation. It just so happens in this case, when you're rolling a die, it's only going to be 1, 2, 3, 4, 5, 6. If you had a 6-sided die, and instead of 1, 2, 3, 4, 5, 6, it was labeled 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, then those would be the specific values that it takes on. Okay, so the other type of random variable is called, well, let's look at a different situation. If we were looking at heights of humans, and after doing a Google search here, I found out that the shortest human ever recorded was 22 inches tall, and the tallest was 8 feet 11 inches, which is, if we do the conversion, that would be 107 inches. So if we call this random variable, I'll call it H, right? H is going to be somewhere in between those values. True, we could have a human shorter than 22 inches eventually, and a human taller than 8 foot 11 inches eventually. But right now, we're going to say those are our limits. Now, there's no way that we could list all of the heights out, because not only is this a wide range from 22 to 107, but you could also have heights of, say, if you take my height is, I'm 5'10", so my height is 70 inches. But if we had very precise tools, maybe my height is actually 7.1 inches. And maybe if we had even more precise tools, maybe we could measure my height to be 70.0934, who knows how precise we want to get. But the point is, this variable is not taking on specific values. There's an infinite number of values between 22 and 107 inches. This is what's called a continuous random variable. Okay, so takes on an infinite amount of values on an interval, right? So we have to make sure that we got some boundaries here. So we're specifically, this video is about density curves. The density curves that we're going to be looking at are regarding continuous random variables. Okay, so there's nothing wrong with discrete random variables. We're just not looking at them at this particular moment. So a couple things that I want to address here is, let's look at a similar situation where we have, I'm going to draw a distribution. And let's just say from, I'm going to come up with a situation just like the discrete random variable, where we have values 1 through 6, 5, 6, okay, and let's go all the way to 7 since it's numbered to 7. And this thing is 1, 6 high, okay, and what we're looking at here is a uniform distribution, right? We've seen this before. We talked about this when we were talking about shapes of distributions. So in this particular case, this uniform distribution is regarding a continuous random variable. So now these particular values, we can take on values such as 1.5, 1.8, 1.923. And, maybe the situation is completely different. Maybe we're looking at the amount of time it took to walk from students' dorm rooms to class. And it was anywhere between, 1 minute to 7 minutes. And we know that this is going to be continuous, just based on the situation, because minutes is a measure. Okay, it's a measure that you can cut into infinitely small amounts. So here we have our distribution, and one thing that we want to look at is that if we're looking at a density curve has a special property, and the special property is that the area underneath the density curve always equals 1. Now, the reason for that, you can kind of think of 1 in terms of percent, right? If we turned 1 into a percent, that would be 100%. So the area under the density curve, what we're basically saying is 100% of the area under the curve is under the curve, which is sort of a foolish way of thinking about it, but it's true. 100% of the area under the curve is under the curve. So that allows us to do certain things. I have 1/6 written here. Let me just erase that for now. Okay, so, oh boy, I just erased a large part of what I just drew. Okay, so let me scroll down and let's do one of the problems. Okay, so here we have an example. A game that is sometimes played at baby showers asks the guests to cut a length of yarn that they believe will best measure the distance around the baby's bump. At a particular baby shower, the length of string cut by the guests was uniformly distributed over the interval 40 to 50 inches. So A asks, what height must the density curve have? Justify your answer. So we could think of this as having a vertical axis, and on that vertical axis, we can think of it as being relative frequency. Or relative frequency, we know, is just a fancy term for percent, right? Well, another way we could think of this is calling this the probability. So probability takes on values from 0 to 1, just like percents take on values from 0% to 100%. So we could use them interchangeably, and we usually do use them interchangeably. So the question asks, what height must the density curve have? Well, let's look at this, and let's think of this curve, since it's uniform, we could think of that as being a rectangle, right? That's just a rectangle. So I'm going to draw this off to the side so I can mark it up. So if we have a rectangle, we don't know the height. They didn't even give us the vertical axis, so we certainly don't know how high it is. That's what the question's asking us. But we do know the length. From 40 to 50, right, this distance right here, from 40 to 50, it's just going to be 10 long. Okay, whatever the units are, doesn't really matter to us right now. It's going to be 10 long. And we do know that the area underneath this curve is 1. That was the property of density curves that we just looked at. So now if we do a little geometry, we could say that the area is equal to the length times the height of this rectangle. And now we can just substitute in there. We know the area is 1, we know the length is 10, and we don't know the height. That's what we're going to be solving for. Well, if we just divide this by 10 on both sides, we get a height of 1/10. Okay? So, we've answered this question using a little geometry. Part B, about what percent of the guests cut their yarn longer than 48 inches? Let's go up to this drawing here. 48 inches is about here. Okay, I'm doing this in a strange peach color, but we're going to go with it. Okay, so there's 48 inches. It wants to know the percent of the guests that cut their yarn longer than 48 inches. So that's going to be from 48 to 50. So you can see we have another rectangle. I'm going to draw that rectangle from 48 to 50, so that gives us a rectangle that's 2 units long, and we now know that the height is 1/10. Now, in order to find the percent underneath the density curve is the same thing as finding the area. Okay, so the percent is equal to the area. So now we could say the area is equal to length times height, which is 2 times 1/10, which is 0.2, otherwise known as 20%. So 20% of the guests cut their yarn longer than 48 inches. Let's use a different color that's not peach. So now we're going to look at the last part of this question. Calculate and interpret the 25th percentile of this distribution. So I'm going to redraw this distribution down here just so I don't have to be going back and forth. So this was going from 40 to 50. It was uniform. Okay, so that generally is what the distribution is going to look like. And we can envision this as being a rectangle. We know the height is 1/10. So calculate and interpret the 25th percentile of this distribution. Well, we know that this is 10 long. If we take 25% and we multiply that times 10, we're going to know how far in we're going to have to go, right? So 25th percentile means 25% of the values are going to be less than or equal to it. So we're really looking for that value right there, which we don't know. So we're going to find 25% of 10. And I'm just going to write this out here, 0.25 times 10. So that is 250. So that means we have to go to the right of 40, 250. So I mean, we could do quick math. That's 40 plus 250, which is 4250. Okay, so in this particular problem, that means that so I need to go back to the very top here, okay? So that means a yarn length, I'm going to write this over here, the interpretation. Okay, a yarn length of 42.5 inches was longer or as long as 25% of the yarn lengths cut by guests. Okay, so we have looked at, let's just do a little recap. We've looked at density curves. Okay, density curves involve continuous random variables. We've looked at uniform density curves. Again, this was a uniform density curve. It's all at the same height. That's what that means. We've learned how to find the height of a density curve, how to find a percent of a uniform density curve, and how to calculate and interpret a percentile of a uniform density curve. Okay, I'm going to stop there. In the next video, we're going to be talking about the normal curve and the empirical rule.